All right, so here's the official topic. We're still on the Net Plus summary, essentially. So we're down to wide area network technologies and protocols. T1, these are telephone company lines. T1 and T3 used to be bundles of copper. Now they run on some other cable infrastructure. But the point is, like fiber optics or possibly even coax, I'm not sure about that, but I know some of them run over fiber. So T1 gives you 1.5 megabits per second point to point and enough to carry 24 analog phone lines. T3 has 45 megabits per second. Europe has comparable ones called E1 and E3. And these are for one point to one point, so you would get them to your ISP from a company that needs a lot of bandwidth. And if you want even more bandwidth than that, because you're really a big company like Yahoo or Google or something, then you go to SONET. This is an optical network by fiber optic cable, and it comes in really big sizes. You can get gigabits per second and so on. All right, a frame relay is a layer 2 protocol used to break a large bandwidth into small chunks. So you could, if you're an ISP, you could lease out certain amounts of bandwidth to different people so you make logical connections over a single physical connection called virtual circuits. And so you create these things called a permanent virtual circuit that's always connected, or a switched virtual circuit that sets up for just one call and then terminates after the call. And it identifies these things with data link connection identifiers. X25 is an older packet switched WAN protocol, but it's been out of date for a long time now. You're not going to see much of it in modern systems. ATM is another wide WAN technology that sends 48 bytes of data and 5 bytes of address in 53 byte cells. These tiny cells are so you can intermix data. You never have to wait for a chance to add data to the line with a high priority signal. And there's another one called Switched Multi-Megabit Data Service, which I think should be SMDS. This might be wrong. Anyway, another older one. You're not going to see much anymore. And asynchronous transfer mode. That's the one with the 50. Wait, that's the one you said here. And then the MPLS. This one you do see, multi-protocol label switching. This forwards WAN data using labels instead of addresses, and therefore you can carry many types of traffic all mixed on the same network. So it's the kind of thing an ISP might want. SDLC is a layer 2 WAN protocol that, like most of them, are layer 2. They connect from your location at your company up to the ISP, point to point. And this uses a polling system like token passing. And then there's high-level data link control, which is a successor that adds error connection and flow control, and has a normal response mode, an asynchronous response code, and an asynchronous balanced mode. All right. And then there are converged protocols which put multiple services over the same Ethernet network, storage, voice, industrial controls, ordinary internet traffic, all mixed. They call that convergence. And DNP3 is an open standard used by the energy sector, electric sector largely, and it's intended to be interoperable between different devices. And the smart grid technology is maybe using this, although one I've heard was using another link-to-link grid protocol. But anyway, this is the attempt to bring utility electricity delivery into the 21st century. Electric power is very difficult to handle because you can't store it. So you have to always generate the amount of power people are actually using right now, and as people turn devices on and off, the amount of power they're using changes, so you have to be constantly adjusting how much power you're creating to go into lines. It's quite complicated, so that's part of this smart grid thing. Let me check for comments in the Twitch. Aha! Pirate Software is the company. Jason the Whoreholic. I don't know that one. All right. Good. All right. Yeah, everything's fine in Utah. We taught our workshop this morning. All right. So, so DNP3 is a multi-layer protocol over TCP/IP. It now has secure authentication. The original version was very vulnerable, like all industrial protocols. And here's the current standard that allows you to have public key infrastructure. Then there are storage protocols to handle storage networks, which is network attack storage and storage area networks are the big things. Fiber channel over Ethernet is the most common one you hear of. iSCSI is another, and these are used for storage area networks, so you can have large amounts of data on the network. Typically for enterprise class things like cloud machines, you have the processing done in one location and the storage in another network. And so fiber channel over Ethernet uses special cables and hardware. FC over E Fiber Channel uses special cables. Then FCOE uses standard Ethernet cables, and Fiber Channel over IP is another way to do it if you want to spread your data further apart and actually go through layer 3. By the way, Fiber Channel does not necessarily use fiber optics. The fiber is just the fact that there's a whole bunch of parallel lines connecting all these devices in a room that looks like a fiber. iSCSI uses high layers of the TCP/IP suite for communication, so it can be routed and lets you have storage over a wide area network, and it addresses the storage units with logical unit numbers. And you can make a virtual SAN. Now, a normal SAN is a storage area network using proprietary hardware and software with all the storage in one room typically. You can make a virtual SAN like a virtual LAN, so you create something that appears over the network to be a SAN, but it is in fact something distributed over a wider area. Voice over IP is what we're using for most telephone calls now. It uses real-time transport protocol to carry the audio and video, and session initiation protocol for signals like ringing the phone and picking up the phone. There is a secure version of real-time transport protocol which provides confidentiality, integrity, and secure authentication. Most voice over IP systems turn off the encryption to get higher quality of the call, but of course it would be more confidential if you left the encryption turned on. So voice over IP typically saves money. In companies, they advertise it as saying you don't need separate phone and IT networks, but in fact, that's people say in practice, you do usually have to upgrade your IT network to carry all the traffic. Therefore, your phone traffic is exposed to network attacks. This is very much like the flaw in operational technology, where you have industrial equipment, but now you connect it to the internet, so now it's susceptible to hacking over the internet, which it wasn't when it was not connected to the internet. And like the RTP provides little or no security by default. You can use Wireshark to eavesdrop on a call if the encryption is not in use. So software-defined networks are where you remember, if you have local area networks, originally they were cables connected to a switch or hub, so it was all the devices within one room. But a virtual local area network could then make a local area network from devices anywhere in the network in separate rooms or buildings that appeared to be on the same network. And that's the same thing with software-defined networks. These create virtual routers, and the control plane makes routing decisions. So you can make routing decisions remotely and customize networks. So not only are your machines virtual, your storage is virtual, your local area networks are virtual, and your other networking features are all virtual, running through a virtual router and such. This dissociates the logical connectivity of your network from the physical connectivity of the hardware. And the most well-known software-defined networking protocol is OpenFlow. It gives you a central controller to control all the switching rules. All right, so that's some wide area network protocols. Let's look at a Kahoot. Just MAN, CAN, WAN, and LAN. Well, it still is just MAN, CAN, WAN, and LAN, and these are the details of the WAN part of it. There are all these funny protocols just for WAN networks. I remember finding them sort of overwhelming when I first learned them in Cisco class, because you don't have much hands-on experience with these typically. They're used at ISPs and to connect to ISPs. Anyway, we want 4F, which is this one, I think. It is. Make sure it's F we're looking for. It is F. Good. Okay. Yeah, the Book of Mormon. The only evidence of the Mormon Church I've noticed here is that when we go for breakfast, there's coffee, and we're the only ones getting the coffee. Nobody else touches it. Anyway. All right, so which link carries 45 megs per second? Yeah, that's a T3. Not ATM. ATM can carry, I think, more. I'm not sure, but it's certainly true of T3. All right, which one is a storage protocol? Fiber channel over Ethernet is storage. So you connect to a storage device over the network. All right, which protocol is used by the energy sector for SCADA devices? I know this one because I wrote some hands-on projects for it. Yeah, it's DNP3. All right. All right, what's the most well-known SDN protocol? Software-defined networking uses OpenFlow, a name which makes sense. It's pretty descriptive of what it does. Well, I have to tell me who they are. Root. That I know who that is. Good. Let's go back to the slides. All right, so wireless local area networks. One big issue is denial of service. If you're in physical proximity, you can launch denial of service attacks. You can just pollute the wireless spectrum with noise, with a noisy motor, or you can send deauth frames, and there is no known defense against these attacks. That's a flaw of wireless networking. It's pretty easy to shut it down by corrupting the wireless band. This works on the bands, two common bands used, 2.4 gigahertz and 5 gigahertz, although I think the very latest protocols began using a higher frequency. But these are the main ones used by all kinds of devices, including most wireless protocols. So they use frequency hopping spectrum, where it uses several channels and hops between them, and this hopefully makes it punch through interference and noise. And direct sequence spectrum is another way to do it. Both of these maximize throughput and minimize the effect of interference. And they use orthogonal frequency division multiplexing, which uses simultaneous transmissions that are different in ways so they don't interfere with each other. And this is the same principle as using wavelength division multiplexing on fiber optic cables. You just send several different colors of light through it at the same time because they'll travel independently, and therefore you can send more total data with multiple parallel streams of data through the channel. And so there's a lot of generations. Here's Wi-Fi 7 and 6. I got 6 at home, works pretty well. They keep getting faster and faster, and they all have an official 802.11 string number. B was the first one from the 90s. Then we mostly moved to G and N, and now it's AC or AX, this sort of thing. All right. So there's 4 modes of a wireless card: managed, master, ad hoc, and monitor. And normally the only one you use is managed, where your laptop is the client, and somewhere there's a router you're connecting to, a wireless NIC, and it is the master, and it tells them what to do. Master and managed are the only ones normally used for normal traffic. Master is for the wireless network, the infrastructure, and managed is for the device connecting to it. So these are the common ones. Then the other ones are used only for special purposes. Ad hoc is for a peer-to-peer network between, say, 2 laptops with no central access point. In principle, you can do that, but it's not a common thing to do. And monitor mode is what you do to sniff wireless LAN traffic, including traffic between other devices. And this is something you'd only do because you're a hacker trying to spy on things, or because you're some kind of network engineer trying to diagnose a problem. Let me check for comments in the Twitch. Roman's not allowed to drink coffee. That is correct. Yep, no coffee, no alcohol. Yep. Anyway, all right. So, all right. And so the SSID is the name of the network that you see when you open up your wireless card and your wireless utility in your laptop and you see these names. These are names chosen by the access point. Some people say you should disable the SSID broadcast so you don't appear on this list. That might stop casual people connecting, but people can still sniff for the frames using something like Wireshark and find them. MAC address filtering is another weak security measure. You can only let people in if they're using certain MAC addresses, but the MAC addresses are sent without encryption, so people can just sniff them again in monitor mode and see what MAC addresses are in use and then clone one of them. So it's again a weak security measure. It will stop casual users from intruding on your network, but it won't stop anybody seriously attacking it. Wired equivalent privacy was originally designed and given this name to try to encourage consumers to use wireless networks when they had an automatic feeling, I can't be safe to just send my data everywhere instead of sending it through a cable. So they added an encryption protocol and said it was equal to wired networks, but that was not true. It's a very flawed form of encryption, easy to hack, and almost extinct now for that reason. 802.11i defined a robust security network, and this is called WPA2. Wi-Fi protected access, and this is much stronger. This is what we're mostly using, WPA or WPA2, which is all much stronger. It uses AES encryption, and it uses something called CCMP for integrity, which gives you a message integrity check. And it's WPA, which was designed for access points too weak to implement 802.11i, uses simpler forms of encryption and is considered weaker than WPA2, but still much stronger than WEP. And Bluetooth, of course, is another wired radio protocol to go short range, typically under 10 meters, although in principle there are other kinds that can go further, but this is typically used to connect devices on your body, like your earpiece to your phone. And uses an E0 symmetric cipher, which is weak. And there are a whole bunch of attacks on especially Bluetooth low energy. Tricks you can cause it to negotiate the length of the key down to 8 bits so it's easy to crack and things like that. There are a lot of attacks on it that people go through. Radio frequency identification is what you put tags on animals or objects. You can have an active RSID tag with a battery that broadcasts. You can have a semi-passive one or a passive one powered by the reader, where it has an antenna that picks up power from the reader, and that powers the chip so it can respond to a challenge. And then you can have a Faraday cage to stop all this wireless signal. If you want to protect yourself from these things, you get wire mesh or a wire screen around a room, and then inside there'll be no radio. You can block it. You can also do this by wrapping aluminum foil around an object. That's why some people make aluminum foil hats to protect their brains from this. And Russell Brand will now sell you like a $300 amulet claiming it's protecting you from these dangerous radiations, which is, of course, a scam. But it's not proven that any of this stuff does harm to the human body, but this is a persistent conspiracy theory or medical attitude that goes around, and people do occasionally try to block the radio signals out of their body, fearing that it's doing them some harm. So let's take a look at 4G. Which is here. The one I heard the most about is suggesting that cell phones are hurting your brain. Cell phones put out a lot of radio, and that keeps coming around again and again. I think there have been some authoritative studies showing that they can't detect it, but that's one people are worried about. There were a few more people coming. I think we had 5 or 6 last time. All right, so what mode connects two devices together like a crossover cable? There's a wireless mode. They call it ad hoc, where two devices connect to each other without connecting to infrastructure like a router. All right, what technology uses simultaneous transmissions that do not interfere with each other? That's orthogonal frequency division multiplexing. Give multiple radio signals that do not interfere with each other so you can send more total data per second. All right, which standard is only on 5 gigahertz? Now you know this one if you've been doing it for 20 years. Probably not otherwise. That was 802.11a. It was more rare because it was shorter range, but it also had a lot less interference because it used a band very few people were using at that time. Anyway, all right. All right, what technology blocks radio signals? Faraday cage. Surround yourself with a screen or mesh, and it'll stop the radio. Right. So, all right. So secure network devices and secure protocols. So repeaters are just something that has 2 ports. In comes a signal, and it sends out a signal, and all it does is increase the voltage to compensate for the drop in a long cable. But a hub is a multi-port repeater. You have many cables coming in, and every time any one of them sends data, it echoes it out all the other ports without reading or understanding the address. It's a connection at layer 1. It lets you have devices connected to each other, but it doesn't have any intelligence. And therefore, it's all one collision domain. It can't send and receive simultaneously, and if 2 of the devices transmit at the same time, their packets will collide and destroy each other, and they'll have to be resent. Using intelligence in the NIC, not in the hub. The hub is completely stupid, like just a crossover cable. Bridges are the next step. You have a bridge in the middle to connect 2 networks, and the bridge is smart. It keeps track of the addresses it sees. It has some internal processing and memory, so it lists what addresses are on this side and what addresses are on that side, and it knows if I get a packet with a destination address on this side, send it over here, and on that side, send it over there. So it doesn't just send every frame out every port. And a switch is just a multi-port bridge where it learns what MAC addresses are in every one of these cables, and it will only send a frame down the cable if the destination is at that location. And therefore, if 2 devices transmit at the same time, they will probably not collide because they'll just go to different destinations. All right. Virtual local area networks, like I said, create this situation virtually. You might have these computers in one VLAN 1, the computer VLAN, and these in the server VLAN. So even though they're all physically connected to the same switch, they are not in the same local area network because the network has extra tags added to it by the switch to tag it on what virtual network it's in, and they don't regard these as the same network. So port isolation is another way to do it. Typically only 1 port on a managed switch can communicate to the uplink, and that forms a private VLAN. This is what you'll find if you go to Starbucks. If you connect to the wireless network and then run something like Nmap to do a port scan, you will find that you and the router are the only devices on your network. Every customer is on their own virtual network, so customers can't connect directly to each other and access each other's shared files and such. It's very useful in modern multi-tenant environments. In the old days, everybody with cable modems could see all the shared files and everybody else in their neighborhood because all the cable network didn't isolate things here. Now, modern networks do. Span port is a port that is supposed to send an extra copy of every frame out this port so you can send it to a monitoring or analysis system. The problem is that port is probably not any faster than the other ports, so if the others are all running at full speed, they won't be able to keep up with the traffic. They will miss some of the frames. That's why a more professional solution is to buy a special network tap device to make a copy of all the packets on the network. And that's here. Network tap is the more professional solution. This way, you typically can keep up with the network running at line speed, so you can then connect a sniffer or network intrusion detection system, which gets a copy of all the frames. So routers are at OSI layer 3, and they can lift network off one local area network and move it to another, like take your local area network and move it up to your ISP to get to the internet. They route things based on IP addresses to find the physical location of the device they're trying to connect to. And you have a default route on a home network that's a stub gate. If you're a stub network, you're an end. There's only one path out of your network. That's the default gateway, and all traffic goes out that way. That's a typical home network. So you have some local devices here, and they're connected to the router, and the router is the only path to the internet. So all these devices have a default gateway, 192.168.1.1, and that's the address of the router. So anything that's not on their local area network, they send to the router, and the router will send it off to the internet to find whatever you're trying to talk to. So there are routing protocols used to adjust the path of the router. Here you might have multiple routers out here going to different offices and the home center here, and they're all connected by T3 and T1 lines. And if a link goes down, there might be another path to get where you're going. Like if you want to reach this office, but this T3 goes down, then you can still get there by going to here and over there. And so these routers have to learn to use an alternative path, and that's what routing protocols do. The routers send traffic over the network, telling each other their state, what networks they can reach, and they learn to compensate for changes in the network and dynamically route around obstacles. Interior gateway protocols are what you mostly see inside companies, things like RIP and OSPF, and the exterior gateway protocol, the only one I've ever heard of, is Border Gateway Protocol, which is used to route traffic from one entity on the internet to another, like one ISP to another ISP. All right, so distance vector routing protocols are the old ones designed for really old hardware, like in the 80s and 90s, and so they didn't actually keep track of the whole network. They didn't have enough memory and processing to handle that. They just said port 1 will reach AT&T after 2 hops. CCSF will be 3 hops out port 2. So they only know what they can reach and how many hops it is to get there. They don't even know how fast the network links are, and this turns out they can easily be confused. Just as RIP was the protocol that did this, and it's subject to routing loops, where you'll send a packet and the packet will just go back and forth. Here it goes to 101, 103, 101, 103, because the two ends are confused, and they send traffic. They each think traffic is at the other one, so this can fail. This is why you need the TTL parameter to notice how many hops it's been, because it is possible for poor old-fashioned routing protocols to lead to routing loops where packets really do just go in a circle and never get anywhere. That's the old and inefficient system designed for very weak routers. Distance vector used hop count as a metric. It would always prefer to send things out the path that has the smallest number of hops, which would only make sense if all the hops were the same speed, which they're not. It only sends updates every 30 seconds, so it can take a really long time to adapt to changes on the network. All right, so they added things to stop routing loops like split horizon, where a router won't echo back a route to the router that originated it, to try to prevent out-of-date updates from propagating through the network and causing routers to go back to an old condition. And poison reverse also doing this, and a hold down timer. These are all attempts to solve the problem that in RIP, since it only sends an update every 30 seconds, and that is then echoed by the next router and the next router, there can be really old, wrong information still propagating through the network, telling routers to do the wrong thing for quite a long time. All right. So now most people use link state routing protocols. They're for modern hardware that has more memory and processor. So each router knows the whole network diagram, and they understand the speed of each link, and they can choose the fastest route. And if something goes down, they can figure out how to route around it without having to wait for some 30 seconds for an update. So it takes more power, but it converges much faster and is much more accurate than RIP. OSPF, Open Shortest Path First, is the open link state routing protocol, not proprietary, that a lot of people use. And there's a EIGRP, is Cisco's proprietary one that does the same thing. And I mentioned before, Border Gateway Protocol is used on the internet to route between autonomous systems like ISPs and large companies. So this gets you a large distance over the internet from one network to another. All right. Let's try another Kahoot. And let me check to see if there's any comments in the Twitch. Nothing new. All right. So 4H is here. All right. Okay, which device operates at OSI layer 3? That's a router using IP addresses. All right, which device moves packets from a local area network to the internet? That's also a router. That's what it does. It lifts packets off one local area network with MAC addresses and sends them off to the internet, another network. Which protocol uses hop count as a metric? RIP, the first oldest routing protocol, measured the quality of a connection by how many hops it would take to get there. All right. Which is the interior routing protocol that converges rapidly? OSPF, a modern replacement for RIP. All right, so then we'll talk about firewalls. The oldest firewalls were just packet filters where they would filter based on a single packet, so they would just block certain ports or protocols or directions. So you'd have a packet filter where you send a request and you get a reply, but if this device tries to send you something, it will also come in because it has the same protocol. So since you let replies come in that you asked for, replies that you didn't ask for will also get in because it isn't stateful, it doesn't remember any history. So stateful firewalls are far more common now, like Windows has this. So now it knows the past. So if you send a echo request and you get a reply, that gets through. But if a reply comes in and you didn't request it, it doesn't get through because it remembers the state. And if this is data you asked for, it's allowed through. But if it's data you didn't ask for, it's blocked. Proxy firewalls break the connection in the middle. So instead of having a firewall that lets you, a stateful firewall lets you do a SYN, SYNAC, ACK and connect to a website, you're not allowed to connect to any websites. The firewall absorbs everything and then retransmits on your behalf. So you do not make any direct connections to any internet servers. And the advantage of this is they can block certain things here, like games and malware sites, and then you'll never get to them because the firewall will not let you go to them. Also called a proxy server. All right, an application layer, proxy firewalls can work at the application data so they can filter traffic based on data that is way out of all the addresses, like URLs that are way up at layer 7, and so they'll be able to look, perform what they call deep packet inspection, look at any data anywhere in the packet to decide whether to allow or deny it. There are also circuit-level proxies that operate at OSI level 5, so application layer data is passed along. SOX is one using port 2080, and that's what Tor uses, the anonymity network. A bastion host is an old-fashioned idea that has now come back. They're now on Azure. This is where you add an extra server just to protect your device from the internet, like a firewall. So this device has to be running on a hardened operating system that provides a specific service. And in Azure, Microsoft has discovered that remote desktop protocol used to remote control a Windows machine is very unsafe and shouldn't be connected directly to the internet. So they recommend that you use a bastion host to protect your Azure server, which will take the traffic and use another protocol, I think SSH, to connect to protect the device behind it. A dual-homed host is a host that has two networks. And it decides you have to first you're coming from the internet, first you have to log into the host and then access the trusted network from there. So this was what people used before firewalls. A screened host architecture forces traffic to go only to the bastion host, and then you only get to the trusted network if you survive the tests of the bastion host. The problem is this is a single point of failure. If the bastion host goes down, you lose the network is you're going to lose connector to it if it fails closed. If it fails open, the network becomes unprotected. DMZ is something many people do. You break your network into segments of different security layers. The simplest one is where you just have two security layers. You have a trusted network here, and then a semi-trusted network here for public things like your web server and email server. And so internet traffic passes through a rudimentary scan just to remove the most obvious attacks. Then they can reach your public resources, but anybody who wants to reach your private resources has to go through more stringent testing, such as, for example, proving that they're an employee of the company by logging into a VPN server or something. You can do it with one firewall. This firewall can have different rules, letting everybody pretty much go here, but only the most trusted people go here. And a modem, of course, takes binary data, turns it into analog signals that can be carried on an analog phone network. If anybody has those anymore, the only kind of these I see in use anymore are cable modems in America, which do the same thing. They turn your network traffic into analog cable TV traffics. So a DTE is a user machine like a laptop or phone, data terminal equipment. Data circuit terminating equipment is the end of an ISP's network like a router. And DMARC is the point where these two meet, where the ISP's responsibility ends. So the ISP sends cables to your building, then it goes to a junction box, which is the DMARC. Then you have internal Ethernet that you lay reaching your networks, and so you're responsible for the internal cables on your side of the DMARC, and the ISP is responsible for the cables and devices on their side of the DMARC. All right, so the CSU, DSU is a synchronous signal. carried by the connection to the internet. So you have a clock rate, and the DCE device sets a clock signal, and the other one follows the clock. So it's not the kind of network we normally use on local area networks, but it is used to connect two internet service providers. So there's secure communication types. There's authentication protocols and virtual private networks and ways to access devices remotely. So authentication protocols are intended to prove who you are. The earliest one was PAP, Password Authentication Protocol, that would just send a password without encryption over the internet. This is, of course, really dangerous. Anybody can sniff it. If they can get a copy of that traffic, they can just replay the password they stole. So this is very bad and shouldn't be used anymore. CHAP is the step up, where instead of sending the password directly over the internet, the server sends the challenge. The user adds the challenge to the password and hashes the result and sends the hash. So the server can do the same calculation and verify that the hash is correct, but the thing sent over the internet is not plain text password. So this is better. All right, but you do have to store the password on the server. 802.1x is port-based network access control, and this has extensible authentication protocol that can be used for a lot of different services. So a lot of different ways to authenticate. You have an authentication server, and a supplicant is the device trying to connect. The server authenticates it, and you have an authenticator, which allows you to connect, and authenticate and connect to the network. So you start here trying to connect. You then talk to the authenticator. It talks to the authentication server, which is something like a radius server, to decide if the credentials you set are correct. And if they're approved, then you get access granted to the internal network. That's the idea. So EAP MD5 is an old one, not considered safe anymore. LEAP is a Cisco proprietary attempt to improve WEP. It's also considered out of date and unsafe these days. It's subject to offline dictionary attacks. EAP Fast is considered quite good, designed by Cisco to replace LEAP. And EAP TLS uses, of course, TLS, the stuff we use for HTTPS connections using the public key infrastructure. It requires clients on both sides, which is very secure but complex, and it used to be considered costly. Now, of course, everybody can get free certificates from Encrypt Now, I think is the name of the company, something like that. But anyway, it's still not common for clients to have a certificate, just the server. And EAP TTLS is Tunneled Transport Layer Security. This allows you to use a client to use a password instead of a certificate. Easier to deploy than the one with a certificate, but of course less secure because a password can be guessed much more easily than a certificate can be forged. And there's PEEP, Protected EAP, which is similar. So these are authentication protocols in common use. Let's try another Kahoot. 4i. And here you get the way the CISSP tends to be. All these things, and you only know the simplest few facts about them. You'll learn hundreds of terms and a little bit about each term, a mile wide and an inch deep. Well, I don't understand that one. 29544. Oh, it's this number. Okay. Perhaps a bunch of people have fallen asleep. Check and see if there are comments in the Twitch. Yeah, let's encrypt. That's what it was. Okay. There aren't a bunch of people saying they can't find the Kahoot or anything, so I'll wait a few more seconds. See if we got any more players. All right. We will carry on. All right, so which firewall uses only the headers to allow or deny traffic? That's a packet filter. It just looks at things like the port number and that's it. Very simple and not very effective to stop modern attacks. Which device runs at OSI 5? That's a SOX proxy. Which system provides port-based network access? That's 8021X. One form of it just limits which physical plug in Ethernet switch you can plug into, which port you're allowed to use. And which one of these is vulnerable and should not be used? Leak, a vulnerable attempt to improve WEP, which is still not good enough to be trusted. So, all right, we